All right, everyone, I'm going to be talking about Lab 7, which is on the ideal gas law. This lab's actually pretty short. I think it's the shortest lab of the entire quarter. It's only 2 parts. Um, but really quickly, like the first part of the lab just introduces what an ideal gas is. And the main aspect of an ideal gas that you should try to keep in mind is that an ideal gas is a gas of atoms or molecules that do not interact with each other, which means that they're not hitting each other. They don't have, some sort of like electrical repulsion or attraction. I know you haven't covered electricity and magnetism because that's next quarter, but like they don't exert forces on each other. That's the main thing with an ideal gas. So if a gas does not exert forces on itself, like the individual atoms within the gas, if they don't exert forces on each other, then it's an ideal gas. And so, the ideal gas law that you've learned in chemistry and in this class is PV equals nRT. So, one thing to note is that they tell you R equals 8.31 joules times, or joules divided by mole Kelvin. So this is true, but this is only true if you measure the pressure in pascals. So, like another form of this equation is PV equals nRT, where R is like 0.0821, and that's only if you measure pressure in atmospheres. So if you're going to use this 8.31, just remember you have to measure pressure in pascals, or like the shorthand is Pascal, like this. And then also temperature is measured in Kelvin, not Celsius. So like if you were like using these numbers here, you would have to convert 101 kilopascal to Pascal, so it'd be 101,000 Pascal, and then this 20 Celsius, you would add that to 273.15, I think. And so this 20 Celsius would be 293.15 Kelvin. All right, and so, and also the small n is the number of moles. All right, and so the experimental apparatus for this lab is really simple. So all you have is like a syringe here, and then that syringe connects to a pressure and temperature sensor. So the pressure and temperature sensor are both in here. And then this will connect to Capstone. And then, in Capstone, you can do whatever measurements you need. One thing to note is that the lab will say to like disconnect the syringe here from this device by using this white like couple here. Do not do that. I mean, just this like white plastic is just like easily breakable, so it's easier if you just unscrew the clear plastic here. So if you unscrew the clear plastic, it'll come off really easily. It's even easier to disconnect than using this white plastic connector, in my opinion. So don't use that. Use the clear plastic. So the first part of the lab is you're gonna take your syringe here, and you're gonna have it disconnected using the white plastic. You're gonna fill the syringe up to 50 milliliters, and then you are going to reconnect it, and then you're gonna push the syringe down to like some location that you can hold it comfortably. So like, I don't know, 30 milliliters or something. Whatever you feel is best. And then you're gonna wait like approximately 15 seconds. So it says to wait about 15 seconds, and that's just so that the temperature normalizes again. Essentially, like if you press it down really fast, the temperature is going to increase inside the syringe, and so you want that temperature to go back down to room temperature. So you're going to wait 15 seconds, and then you're going to let go of the syringe. It's going to bounce back up to like 50 milliliters again, and then you're going to wait for the temperature to normalize again, and then you're going to stop taking data, and you're going to do some data analysis that the lab walks through here. And then you're going to calculate the initial number of moles and the final number of moles from your data. And then when you're done with that, you're going to redo the experiment, but with an initial volume of 60 milliliters instead of 50. All right, and then the second experiment is somewhat similar. So you're going to, again, set the syringe to have 50 milliliters of air inside initially, and then you're going to compress the syringe to 45 milliliters, wait for the temperature to stabilize again, and then you're going to push it down to 40 milliliters, wait for the temperature to stabilize again, and you're going to repeat that over and over, all the way down to 25 milliliters in 5 milliliter increments. And you're going to do some various data analysis that I walked through, such as like using the multi-coordinate tool to identify pressure values. You're going to record these in your notebook. You're going to do this different stuff. You're going to end up graphing volume versus 1 over pressure. All right. And so, the lab walks you through most of it. And you're going to then go ahead and repeat that experiment for for an initial value of 60 milliliters down to 30 milliliters. Again, also in 5 milliliter increments. And then, you're going to answer some questions. And then the first short summary question is like, why is the ideal gas law an important relation? What is an ideal gas? So I explained what an ideal gas was at the beginning, but just obviously it's important because it describes just describes gases in daily life. Because like the lab manual mentions it somewhere, but typically we can think of a lot of different we can think of gases in like normal conditions as like being pretty close to being an ideal gas. And then it asks, in what physical systems can the ideal gas law be assumed to be valid, and what physical systems will the ideal gas law be invalid? Why? So like, are there systems where like you can't even use the ideal gas law at all? And so what would those be? And then also it says, discuss the importance of the universal gas constant. And then where else might it be useful? Why? And then they give you a hint to think about energy and, why or how might it be useful in the context of energy, or maybe some other equation relating to energy, or just a concept relating to energy. Just, it's a semi-open-ended question. But hopefully this lab goes well. I think it should be a lot shorter than the last one and more fun as well. So have fun.